Hello everyone. So today we will continue our discussion of chapter number 1, and today we're going to talk about chapter number 1 part 3 of digital media course. So in the last class we discussed the binary digits, bits. We had a detailed discussion about the bits, how we can encode a data or information in the form of bits. So we will continue from there and we'll see how we can encode different kind of information like numeric numbers, numeric values, textual data and things like that. So firstly, we will start with the review of bits. Over last discussion. I'll just give you a quick overview that what we discussed. Then we will discuss how we can use the bits to represent the information. So using of bits to represent data or information. So what kind of information we can encode, because computers they don't understand the human language. So if you want if you want to communicate with computer, you have to encode the data into machine language or into the binary data. So we will see how we can use bits in order to encode, for example, numeric values like the numbers. We will see how we can convert a text into binary. Then we will see images, sound, audio, and program instructions. So we'll see how we can convert all these values like numeric values, textual data into binary, how we can convert them. The third agenda item, we'll see what is a file. We'll discuss the file size, the disadvantages of having a large file, disadvantages of large file size, and lastly, we'll discuss how we can reduce the file size. We'll discuss different strategies to reduce file size. So these are the three main agenda items that we're going to talk about. So let's start with the first agenda item, review of the bits. So if you remember in the last class, we discussed that computer processes the data, stores the data in the form of bits. And bit is the smallest entity which computer can process. So computers understand, or you can say process or store data in the form of bits. And the full form of the bits was binary digits. And these binary digits or bits, they can have two states. It could be 0 or it could be 1. So we just have two states to represent a bit or a binary digit, that is 0 or 1. And that is why number of possible values which we discussed, like number of different colors or things like that, number of information, x for example, 2 raised to power n. Why 2? Because base is always 2 for digital systems. So whenever you design any digital system, you will see the base is always 2. Why 2? Because there are two possibilities for a bit. A bit can be 0 or a 1. So that's why we use 2 raised to power n. And where is n? Well, like this n is number of bits to represent a data, a specific type of data. For example, let's say if your color can be represented in 3 bits, if let's say 3 bits represent a color, so how many different colors we can generate? 2 raised to power 3 is equal to 8. Okay, so if 3 bits like 0 0 0 represent a color, let's say a black color, and 0 1 0 it represent white color. So by doing this, we can create 8 different colors. That's basically what we discussed in the last class. So this is just an overview that what we talked about in the last class. Now let's move on and see what is how we can use bits to represent a numeric value, a number, textual data, images, and sounds and other stuff. So let's see how we can represent a numeric value first. So numeric values are basically like the numbers. For example, 1, 2, 3, 4, and all that. So numbers can be mainly, if you interpret the numbers can be of two ways, of two type. Number can be a decimal number, a decimal value. Base 10. Decimal value is basically the numbers which we use in our daily life. For example, 1, 2, 3, 4, 5, 6. So decimal value are the numbers which we use in our daily life. The numbers that we use in our daily life are called decimal values, decimal numbers. These numbers, there are 10 unique numbers, and then the rest of the numbers can be created by using the combination of these unique numbers. Like it started from 0, 1, 2, all the way to 9. So these are the unique numbers that we use in mathematics, or we call them decimal values. Now, these numbers, like all the way, I mean, like for example, just to give you an idea, like 19, 20, for example, 73, all these numbers are called decimal values, or you can say numeric values, but representation is decimal. Now, the thing is, or the problem is that computers, if you want a computer to understand these decimal numbers or these values, computer cannot understand it. If you want computer to understand 19, so 19 has to be represented in 010101 format, because computer understand only binary language. Like, of course, there are different type of data that we use in our daily life. We use numbers, we use text, images, sound, and program instructions. And these are the different type of information which we want computer to process. So if you want computer to process a number, a text, image, sound, or program instruction, you have to convert that particular number into a language which computer can understand. So that is why we need to do some sort of decimal to binary conversion. And if computer wants to communicate with us, computer has to do decimal to binary conversion or binary to decimal conversion, like reverse. So let's talk about how we convert or encode the decimal number which human can understand, like for us, which human can understand, how we can convert the decimal number into a binary number so computer can understand that as well. So in order to do that, let's take an example. So for example, there's a number 19. Let's take 19 number. So 19 is a decimal value. We need to convert 19 into binary. Let's do it step by step. Let me just tell you, there are many ways to do that. Many ways. I mean, different methods. In our class, I will tell you 2 or 3 different methods. But here, I'm going to actually tell you one of the hack, like the simplest method through which you can convert decimal to binary and binary into decimal very easily. So let's say this is the number which you want to convert into binary. In order to do that, please remember one thing. To convert this into binary, into digital system, so what we have to do, we need to look at this because it should be represented with 2 raised to power something, right? 0, 1 and all. So first of all, we need to write down a sequence here. 2 raised to power 0, because it's going to be digital. 2 raised to power 1, you need to just, I mean, regardless of whatever the number is given to you, you need to start writing these things. 2 power 2, 2 power 3, 2 power 4. Now, and 2 power 5, for example, and you can actually take it all the way to 2 power 20, I mean, if required. So 2 raised to power 0 is 1, 2 power 1 is 2, 2 power 2 is 4, 2 power 3 is 8, 2 power 4 is 16, 2 power 5 is 32. If there would be 2 power 6, it's going to be 64. I mean, you might have seen this, like iPhone or any digital device. You will see all those devices, the size of those, storage size of those devices would grow in this fashion. Like you might have an iPhone 32 GB, 64 GB. Why don't they offer you a 100 GB iPhone? Because they cannot create it. If you want to create any digital system, it will grow in this particular fashion. Now, the thing is right here, since the number is 19, if this number 19, I mean, if it is, this number 19 is smaller than 32, like the next 32, so we don't need this bit, in fact. Okay, so for example, if this number is 33, then of course we need it. Okay, we don't need the next one, 64. But if this number is smaller than the 32, then of course we need to discard it, okay? For example, let's say, I mean, you can have it, it doesn't make any difference, but it will be extra work for you. So for example, if the number is, let's say, if it would be 7, then in that case, we don't need 8 even. We don't need, for example, this 16 as well. Are you getting my point? So let's say, for example, we got 19. So we need to create 19 by using these combinations. We need to add these combinations, like these values, to make 19. How we can do that? Let's say to make 19, we need 16. We need 16. Okay, so we will put 1 here. Can we add here 8? Because if we add 16 plus 8, what it's going to be? 24. It's going to be 24. No, we cannot have 8 because we need to make 19. So we don't need 8, 0. So let's say we need 4. Can we use 4? So 16 plus 4 will become 20. We need 19, so we cannot have 4. So we don't need this as well. Next, we already have 16. Can we add 2? 16 plus 2 is 18. That's good. We can have it. Can we add 1? Yes, we need add 1. So 18 plus 1 is 19. So we need this. So this value is the binary representation for 19. So 19 is the decimal value. 19 is the decimal value, can be represented by this, and the binary for this is 10011. Let's do it with another example. Let's take another example. For example, let's take a number. Now let's take a big number. Let's take a number, for example, 75. Let's take a number 75. Now we need to convert 75 into binary. Again, 1, 2, 4, like 2 raised to power 0, 2 power 1, 2 power 2 and all. I'm just making it simple. 8, next is 16, double of 16, 32, double of 32, 64, double of 64, 128. Do we need 128? No. Why? Because 75 is smaller than 128. If it is smaller than 128, you don't need it. You will stop it before, because if it is 129, then we need it. So if it is smaller than 75 is smaller than 120, we don't need it. So we need to make 75. We need to find the combination for 75. Do we need 64? Yes, we do need 64. 64 plus. So we need to on this. This bit will be on. Okay, so next, can we add 32? So 64 plus 32, what is the answer? It's 96. Of course not. We don't need 32. We need to make 75. Can we add 16? 64 plus 16, what is the answer? 80. We don't need it. Can we add 8? 64 plus 8, what's the answer? 72. We can have it. Of course, we can have it. 8. 1. So whatever we will add here, we just have to put 1 here. Next is it's became now 72. Can we have 1? So 72 plus 4, it's going to be 76. We cannot have that because we need 75. So we need to make it 0. Still we have 72. We are still at 72. So can we add 2? Yes, we add 2. If we add 2, 72 plus 2 is 74. Still we are less than 1. So what do we need this 1? Yes, we need this 1 as well. 1. So it will become 75. So the binary for 75 is going to be 1001011. So this is the binary, and the decimal value for this is 75. Let's do another example. Let's try for that as well. Let's take a number. Number is, for example, let's take a big number, 131. So number is 131. We need to find the binary for this number. I'm going to write it down again. 1, 2, 4, 8, 16, 32, 64, 128. Again, it is greater than 128. So we will go to 256. So do we need 256? No, because 131 is smaller than 256. We don't need it. We will end to 128. Okay. Now let's see, what would be the binary for that? So we need to make 131. Do we need 128? Yes, we need 128, so we will add it. So 128 plus what? In order to make it 131. Do we need 64? No, it will be too big. 32, too big. So all we need is 128 plus 2 plus 1. So 130, 131. So all these values will become 0, and we just have this and this, like 2 plus 1, it is equal to 131. Got it? So the binary for 131 is going to be, this is the binary. Okay, so what we have learned here how we convert a decimal value into the binary. Now let's see how we can convert a binary into decimal. So let's do the reverse thing here. How we can convert the decimal into binary. Let's try this. So for example, let's say you have a number. Now let's see. We are going to do binary into decimal. I mean, you will be provided with 100 or something like that. You have to convert it into a decimal number. How we can do that? That's very simple again. Let's say the number that you have is, assume that you got a number 10011. You got this number. Question is, convert this binary value into a decimal. A human understandable language like 1, 2, 3, 4, 5, 6. Again, the same strategy. Just put these 1, 2, 4, 8, 16, 32, 64. I mean, if you want to extend it, that's fine. All we have to do is we just start putting the numbers. I mean, start putting from here all the way, we'll put it down here. So 1 here, like this values here, 0, 0, 1. We don't need these two numbers because our number got end here. So what would be the answer for this? We need to find it out. So which values or which bits are on? 16 plus 2 plus 1. So these bits are on only. If you see, like this is on, this is on, this is on, plus 1. So answer is 16 plus 2 plus 1 is 19. Let's do another example. Okay, so for example, you have a number 11011101. For example, that's the number. Start writing the same binary string 1, 2, 4, 8, 16, 32. Or you can, I mean, the easiest way to do that is like, I mean, rather than putting this on the top of it, because this is the value that we have to do. 1, 2, 4, 8, 16, 32, 64, 128. In that way, you don't have to discard. Now, whatever is on, you just add it. 128 is on, 64 is on, 32 is 0, that's fine, we don't add it. 16 is on, 8 is on, 4 is on, 1 is on. 0 and 32, these are not present. So just start adding them together. So we will have 128 plus 64, 128 plus 64. So it's 128, 64, 192, 192 plus 16. 192 plus 16 is 208. Okay, so 208 plus 8, 216. 216 plus 4, 220. And 1, 221. So the answer is, this is the decimal value is 221. You can use calculator to add them all together. So this is the way how we can convert a binary into a decimal value. Very, very simple. Let me just do one more example and then we will move to our next agenda item. Let's take another one. Let's take a small value. So it would be, let's say take a number 40. That's it. This is the number you need to find the binary. Sorry. I mean, we were doing the binary to decimal. So let's do a number. Let's say 100101. Put a number on the top. 1, 2, 4, 8, 16, 32. Whatever is on, just write it down. 32 plus 4 plus 1. So 32, 4 plus 1. 37 is the answer for this particular binary. So this is the way how we convert a binary into a decimal value, right? I believe everybody got it. If anybody will have any questions, of course, we can have a discussion during the class time as well. So let's move on to our next. So to convert, to encode these standard characters, like characters mean, I'm talking about A, B, C, D, and some numbers like plus, minus, etc., etc. How we can convert these textual letters? In order to do that, we use a standard which is called ASCII code. And that's the one which we use in our cell phones as well. Typically in the cell phone, because they support the multilingual, so we don't use ASCII code, we use Unicode for them. But the ASCII codes are typically used to convert the English letters, the characters A, B, C, D, and all into a binary language. So ASCII stands for American Standard Code for Information Interchange. So there is a code for each character. It is already prefixed code, and for all the characters, like all the way from uppercase letters, lowercase letters, some of the special characters, there is a special code for that. And we use an ASCII table. I will show you guys the ASCII table during the class time. So ASCII table, it converts like each character. It could be a special character like A, B, C, etc., etc. Each character is of 8 bits. Like for example, if you have a character A would be something like 00011110001. I just give you example. That's not basically the ASCII code for it, but just to give you example. So each character would be of 8 bits. Now you need to think how many different characters we can encode. If each character, like I'm telling you, each character n is equal to 8 bits. What do you think how many different characters we can generate? So formula, you know that x 2 raised to power 8 is 256 bits. 256 characters. So we can encode 256 different characters using ASCII code. We will discuss that, of course, during our class. I'll show you guys a table as well. For multilingual, we don't use ASCII standard. We use another standard which is called Unicode. It can encode up to 100 different languages. It has the characters of 100 different languages. Now let's see how we can encode the images. An image can be of two types. It could be a vector graphics or it could be a bitmap image. Like for example, .png, .bmp, like the digital images. Those digital images are called bitmap images. These are basically digital images. All these digital images, they are made of pixels. Small boxes, they are made of pixels. Like for example, if you got a picture or something like that, it is basically made of pixels, small box. If you zoom a picture all the way, like zoom as much as possible, you will start seeing small boxes. And each box got a different unique color. So these pixels, they define a special color. And this color value could be represented in the form of bits. We will discuss that in our chapter number 2. So colors, like again, let me repeat, the bitmap images, they are made up of these small boxes which are called pixels. Each pixel represents a color, and that particular color would be represented in the form of bits. Second type of our images, the second type of images are basically vector graphics. Now these vector graphics are basically we use for like Flash, for example, for animation, for logo, etc., etc. The best thing about vector graphics are they don't lose the resolution. For example, if you keep on zooming or make the size big, it will not, there would be no what we call the poor resolution. If you take a printout of a bitmap image on a Panaflex sheet, on a big screen, big sheet, it will lose the resolution. Reason behind it, because vector graphics are basically made of equations. And these equations can be represented in the form of bits. Another type of data which typically we want computer to process, it's the sounds. And sounds are basically sampled. I mean, typically what we do, typically the sound signals are continuous signal. So as we discussed in the last class, in the chapter 1 part 1, we cannot process the continuous information. So what we do is we take samples of continuous signal. So sampled audio, which typically define the amplitude, and these amplitudes are loudness. And all these samples, like these samples, they can be represented in the form of bits. So whatever the samples are, we just round the sample off according to, if you remember, the bit depth and quantization value, we round them off and convert them into binary. Then the musical instruments, MIDI, musical instrument digital interface, through which you can connect your musical instrument with your computer. So musical instrument digital interface, each musical device, for example, piano, guitar, and any other musical instrument, it got a special unique ID, which is typically represented in the form of bits. So each musical instrument has an ID, and that ID is represented in the form of bits. Similarly, each music note has a special ID, and that ID is represented in the form of bits. We will discuss all these conversions in our chapter number 4 and chapter number 5. The next type of data could be instructions, like for example, arithmetic operations. So all these arithmetic operations, for example, these operations could be subtraction, it could be, for example, additions, etc., are represented in the form of bits as well. So we define we have specifically defined some kind of code for subtraction, some addition as well. So this was the second agenda item that we were talking about. Like how we can convert the data or our information into the bits. So we have discussed 5 different type of data. We have discussed the numeric values. We have discussed text values, textual, where we use ASCII characters. We use images. We talked about sounds and program instructions. Let's move on to our last agenda item for today, the file size. Let's see what is basically the file size, what is the role of file size, and if you have a larger file size, what would be the disadvantages. So file size, first of all, you need to understand the file size is basically nothing but number of bits. Like you might have seen, let's say if you capture a picture, so picture file size could be, let's say, 10 MB. So 10 megabytes. 10 megabytes mean each byte has 8 bits. So 10 multiplied by 8 M bits. So what does it mean? 80 megabits. Okay, if you want to convert them. So basically file size is nothing but the number of bits that have been used to encode data or information. So if you have a large file size, like if it has more information, more data, then large number of bits, like more number of bits. So if you have more number of bits, automatically what will happen? The file size will be larger, like 10 MB, 80 megabits, million bits, approximately. So if you make it, let's say, if you have 100 megabyte, mean it has more bits. If you have more bits, automatically file size will be larger. Now, what would be the disadvantage of having the large file size. One of the biggest disadvantages, longer transportation time in the local system. Let's say if you want to copy paste in the local system, so those files which are of large size will take long. Again, longer transportation time over internet. Let's say if you want to upload any document over internet having a large file size, it will take long as compared to the file having small size. Other than that, it's the longer processing time. If you want to apply some processing, editing or something like that, it will take longer as compared to any other. So it will be like if you have a long file, if you have a large file size, it will take longer to process. It will take more time in order to move, in order to get transported. How we can reduce the file size? I believe everybody is already familiar with all those strategies which we discussed in part 1. If you remember, we cannot actually store the analog signal. So what we do is, remember, digitization, sampling and quantization. If you remember, sampling and quantization. So sampling and quantization, which is bit depth, if you remember, like quantization where we round off the value to the nearest level. So if you want to reduce the file size, you can lower sampling rate, like take less sample. Lower sampling rate, take less sample. Like for example, rather than taking 100 samples per second, if you take 10 samples per second, you will have less number of bits. But again, the data quality will get compromised. Lower quantization level, or you can say bit depth. If you have less number of quantization level with which this sample will be rounded off, it will take less space, or the file size will be smaller. These two are not basically the convenient methods. One of the best method is apply compression. And that's what we do. Apply compression. And if you want to apply compression, compression can be of two types. Compression can be lossy compression, and it could be a lossless compression as well. So lossy compression, in the lossy compression, we discard some information permanently. So we discard the information, and that information can never be recovered, which can never be recovered. So please remember, very important thing, if you want to do further editing, we don't use a lossy compression file. Like for example, lossy compression file examples are MP3, MP4, PNG, JPEG. These are some of the examples of lossy compression. But the best thing about most of the lossy compression, especially MP3, because human, what we can hear from frequencies 30 hertz all the way to 20 kilohertz. That's basically over audible, like hearing range, the human hearing range. So MP3, what it does, for example, MP3, if they want to discard some of the information, like they want to discard some of the sample, they try to discard those samples which don't fall in this range. So MP3 discard those frequencies, or you can say samples, which human cannot perceive. So in that way, of course, you're not losing any kind of tangible information. So whatever human cannot perceive, they will discard it. Lossless compression, it does make a difference, but a very minimal. For example, lossy, let's say if you have a 10 MB file, and if you want to make it MP4 file, MP3 file, the file output could be, let's say, 2 MB. But lossless compression will make it 10 MB to 9.7. They try to look for some of the values which, of course, which cannot affect. It doesn't degrade the performance, but lossy can degrade the performance significantly in some of the cases. So that's it about chapter number 2. Chapter number 1, part 3. We have discussed mainly Three things: review of the bits. We talked about all these different type of information, how we can convert these information into bits, and finally we see how what's the file size, disadvantage of the file size, and how we can reduce the file size. So if you will have any questions, so please bring it up in the class. Thank you.